Greetings, this is Gautam Gopan, and on behalf of my fellow co-authors, here to present a paper on Chandrayaan-3, the detection and identification of exomoons and exoplanets in deep space using AI. The launch of Chandrayaan-3 by ISRO will certainly aid the search of exomoons and exoplanets, hereby trying to answer the age-old question that's been pondering humankind for a long time, whether we are alone in this solar system, or is there any other planets that could sustain humanity, just like how Earth has been sustaining for a long time. This laid the foundation to the search of exoplanets. With the advancements of both image capturing and telescopic technologies, we have now access to never ever seen before data, which, when combined with the processing capabilities of advanced AI, paves way to discoveries of new exoplanets and exomoons. This work mainly focuses on how the various technologies and methodologies can be intercorrelated to improve the overall efficiency of the final system. Coming to the problems framed, with respect to the current efforts regarding exoplanet hunting, there exist multiple different techniques that can be utilized for the detection of exoplanets, like studying the radial velocity of planetary objects and observing the transmitting shadows of the planets and so on. Individually, all these techniques have yielded various positive efforts in the past, but a lot of these have a lot of shortcomings that are associated along with it, eventually leading to noise-filled data. The lack of proper referential data points that would mimic the readings of such Earth-like exoplanets have also been lacking in these deep space explorations. The relation with the SHAPE project. The Chandrayaan-3 module was equipped with a scientific equipment named SHAPE, full form of Spectropolarimetry of Habitable Planet Earth, which launched to study Earth from the lunar orbit. The entity was launched to the lunar orbit before the module was landed in, and observing the Earth from the lunar orbit would mimic the observations of a distant exomoon or exoplanet by considering Earth as a possible candidate for observatory purposes. The key role of the module is to analyze and capture the disk-integrated spectrum of the Earth to analyze the polarization signature from various vantage points within the lunar orbit, thereby observing the variations at different phases. This would give us dummy reference points in future relations for deep space exploration. Analyzing the individual methodologies. The Doppler method. This works on the principle that the stars are also under the influence of the gravitational pull of the planets around them, and this happens when both the star and the planet revolve around a fixed center of mass. The gravitational pull results in a slight wobble induced in the star's movement, and by observing this vast wobble, it can be deemed that it plays host to a nearby exoplanet. Now, how do we analyze this wobble? This wobble can be analyzed by going through the light that is emitted from these stars and analyzing the spectroscopy of the light that is emitted. The transit method. This method works on the principle that if a planet is orbiting around a star at a fixed angle and orientation with respect to the center of mass of the existing system, then the planet is supposed to cross in front of the star during its transition throughout its orbit. During this process, the light coming from the star is under observation. Slight variations in the brightness level can be evident. This, when converted into mathematical terms, can be related as the change in flux of the light intensity can be squared to the squares of the radius of the exoplanet divided by the radius of the star that is revolving around. The third method is a direct imaging method. The exoplanets have the capability to reflect light generated by the star planet. This light can be detected by taking direct images of such planets. But unfortunately, due to the huge glare generated by the stars, the light reflected of these planets often go unnoticed. This process is aided with the applications of coronagraphs, which are entities that would help block the intense glare that is generated by the stars. The gravitational microlensing method. This concept works on the principle that a heavier star or a planet bends the space fabric around it, causing the light that is passing through their system to be brightened for a period of time. This variation can be noticed on the graph to the right of the screen, where a small blip originates when the light is bent, and thereby causing a variation in the intensity of the brightness that is being emitted out of the system. The fifth and the most least concept is the astrometry method. This concept works by measuring and keeping track of position of stars, which is marked with other reference stars in the broad line, and the distance from each of these reference points to the stars of the target star is measured and monitored continuously. Any variations in these measurements would eventually let us identify the wobble of these planetary bodies. The only reason that this is the most least method from the remaining four is because these are heavily reliant on telescopic technologies and very hard to measure the variations, as these variations are extremely minute in nature. The drawbacks with the current system. The spatial orientation from the point of observation or the angle at which the target system is observed plays a very crucial role in the identification of exoplanets. In many scenarios, due to the inappropriate orientation of both observation units and the targeted systems, result in gathering of incomplete or noise-filled data sets. This can be observed exceptionally with varying the observation points from in the surface of the Earth to telescopes that are placed on surface of the Earth to the orbital or lunar orbit-based systems. There are huge variations in the data collected due to discrepancies in the atmospheric contributions of the planet. Thereby, having lunar orbit-based observation points will help us minimize the noise that are collected in the overall data. The increased dependency on the host star. There might be planets that are further away from the star and might have been missed out during the direct imaging process, which led to the discovery of the remaining four. This explains the dependency on the host star and the detection of exoplanets. A classic example for this is the new born star, the HR 8779, which in the image that you can see on the right side of the screen has four exoplanets near to it. But there are other bleeps of two bleeps that have popped up in the recent discoveries, which was initially blared out by the extreme glare of the star HR 8779. So therefore, there's an increased dependency on the host star, and the glares often tend to hide these existing exoplanets that are near to the vicinity, thereby leading to them being not discovered. In methods like direct imaging, the glare produced by the host star often blinds the region around its close proximity, often resulting in exoplanets near the star to go unnoticed. The proposed system. The proposed system aims in the integration of the five methodologies that are previously discussed in the above slides. And the advanced CNN-based image analysis can be used to analyze the image captured by direct imaging, increasing the overall efficiency by least squared optimization, grid search, and other matched filter approaches, which can even further analyze the spectroscope of the characteristics of the planet. The lack of proper dataset was one of the again major issues that were concerning the existing exoplanet hunting missions. And since the shaped module would be giving us more data reference points that could mimic the possible data sets that can be associated with an Earth-like planet, the lack of training data sets has also been now customized. Detailing the neural network involves in simulating training data to train deep neural networks to predict single planetary transits. Convolution neural networks can compute local attributes of data using subsampling and convolution when date is correlated with each other. The weights of these networks will also be pre-programmed before the system is being trained, and these weights would be pre-programmed using the existing dummy data that has been collected using the shape module. Four filters make up the CNN1D, each with six weights fine-tuned using the training data. The least square approximation, grid search, and match filter approaches aim to maximize the correlation between the data and simple transfer model, thereby ensuring that there is no gap between the connectivity of the data flow. And in case of any gaps, the other subsequent methods will be pulled in to fill the gaps in the databases. Handling the SNR. The constructive binding of data may improve the signal to noise ratio when individual transit depths are below the scatter. Grid search uses binding by performing brute force analysis over a range of periods, epochs, and durations to look for transits using either the match filter or least square methods. The image on the right side it describes of how the convolutional network is broken down into different steps and how each step is having the max pooling layer, which eventually converts to the final SGD solver. The remaining frame, the system processes light pure data from optical system, processing it through a CNN1D algorithm. The system sensitivity is based on the expected photometric accuracies of tests, aiming to find planets similar to Earth. Again, this is where the data from the shape model will be pulled in for reference points. The transit depth is calculated using the assumption of G-type star with the same radius as the Sun. The CNN1D algorithm can reliably identify the Earth's transit in bright stars, but requires bringing of fainter stars. The next generation of data processing automation is also adaptable in the self-learning, which makes the system extremely volatile in nature, where with add-ons could be that will be easily added on to enhance the overall efficiency of the system. This paper discusses the importance of deep space exploration, focusing on the identification of exoplanets as potential alternative to the Earth system. The proposed system aims to solve the current hindrances faced by individual ideologies by integrating them into a single entity or a single system, allowing for better data flow. Now, coming into the cost effectiveness and the integratability of the work, since most of the solutions that are proposed are software based solutions, the system is extremely flexible and robust as it can be integrated into existing spatial and land based observatory systems. And advancements in the hardware solutions will lead to more viable datasets. Through the various studies and market research that has been conducted for the working of this paper, it is clear that there's a huge scope of development in the field of deep space exploration, aided with the continuous development in the hardware and technical aspects associated with it. Research has to be done on ways to reduce dependencies on the host star, and that should be one of the pivotal points to be addressed in the coming researches. Further developments could aid in orbital or debris removal programs and space contamination. The system's flexibility and robustness will make it easier to integrate into existing spatial and land-based observatory systems. Finally, the work hopes that the information that is gathered through the researches and further researches to come will eventually aid us in answering the age-old question of whether we are alone in this earth, and possibly would even lead to finding an alternative to our Earth-based system. Thank you so much.